Welcome back, everybody. Let's start again. So where do we leave? I'm going through the types. The next type we're going to look at is Booleans. Just like the JSON Booleans, it's true or it's false. There are only two values. Now, depending on the specific dialect or language that you're using, they might take different literal shapes. In the sense, literal is what you write on your keyboard. True, false, but also Y, N, yes, no, on, off, 1, 0, and so on. So there's many different ways you can represent them. But technically, it's always the Boolean algebra with true and false. This is what it's really about. So this is also there. Then you have date and times. Looks simple, very complicated. In fact, it's often underestimated what the effort is to support them. And in fact, when there are new languages and new technologies, they are always forgotten. So people have to add them afterwards and extend the system. But in the enterprise world, dates and times are extremely important. As soon as you run a business, then you need to store them. So there are many different calendars. Commonly, we use the Gregorian calendar with a year that can be positive or negative, a month, and a day, but there are many, many different other calendars that can be used, and some systems might even support multiple calendars. All right, solar, lunar, there are plenty of versions of them. I could actually speak for 2 hours on the history of calendars, but I'm not going to do that. So year, month, day. Then we have the times. So the times is hours, minutes, seconds. So that's what we call the, if you want to shine in a party, it's the hexadecimal system. It means base 60. When you have the minutes and the seconds, 60 minutes in an hour, 60 seconds in a minute. This is how it's done. And then we use a dot for milliseconds and all the way typically to microseconds. I don't know many systems that go below that, except maybe at CERN or in specific applications, but typically we go to the microseconds, right? There have been attempts to redesign the whole thing in base 10 as a decimal system of times, but that never succeeded. So at least it never got popular. So hours, minutes, and seconds. And then you can have that together as a whole date and time and so on. What gets complex in there is the time zones, because you need to also specify if there is a time zone, if there is a time zone, then which time zone is that, like UTC +2 now for summertime right here, CEST. So it's very complex. But the nice thing is that if you have a date and a time, and you don't care what time zone it is, you just want to identify a moment in time, then paradoxically, this is the easiest, because that's called the timestamp. And in that case, the convention is to just give the number of milliseconds since the 1st of January, 1970, which is extremely compact in memory to represent. All right? Then we have intervals. Intervals can also quickly turn into a nightmare. An interval can be, for example, 2 years and 4 months, or 3 hours and 14 minutes, and so on. The problem with interval is the scary wall between the months and the days. As soon as you start mixing and going past that wall, like, for example, 3 months and today, what is 3 months and today? We don't really know, because does a month have 30 days, 31 days, 29, 28? So this is what you should be careful about. Some systems allow it, but you should be careful not to cross that wall to avoid any ambiguity, right? So these are all the possible kinds of intervals that you can have, right? Then we have binary data. Binary data is what happens when you try to store an image or a video or anything as a value in a database, can be even in a relational database, in XML, in JSON. So you store binary data. There are ways to store it more efficiently than zeros and ones. For example, you might have already seen base 16 way of storing binary data. It's when you have all the digits from 0 to 9 and then from A to F. This is base 16. And every alpha numeric character is actually representing 4 bits, right? From 0 to 15. So this is one way. There is also a base 64 that basically is even more compact than base 16, but I'm not going to go into that. It's a more tricky way with all the lowercase and uppercase letters plus the digits, then you add 62, and then you add 2 more characters, and then you add 64. And then it's a way of compacting the representation even more. But anyway, just think of binary as a picture or a video that you can store in HBase or in a PostgreSQL or even in an XML or JSON documents. And then we have null. Null is, how am I going to say? There are so many conventions, and every system is different. There are systems that say null is the same thing as the absence of values. There are systems that say no, null is a special value, and so on and so on and so on. So just be prepared for that. And in some systems, null is even a type that contains only one single value, null, and that's pretty much it, right? But it's there. You probably saw it in Python, in Java. I mean, there's plenty of object-oriented programming languages that also have nulls. JSON has nulls. You saw it in JSON, and so on. All right. So what all of these have in common, all of these types, is that there is the concept of a value space and the concept of a lexical space. The lexical space is the text representation of a value that you see in XML or JSON, or that you type on your command line or in SQL when you want to represent it. For example, 4 here can be represented as 4, the digit 4, or +4 is 0, which means 4 times 10 to the power of 0 in scientific notation, but that's also perfectly fine. 100b means that it's 100 in base 2, right? That's also 4. So you see there are many ways of representing that. These are called literals or literal values or lexical values, right? So this is a text representation. And then on the left, you have the mathematical abstraction of that. The mathematical abstraction of the number 4 as 4 oranges and so on, right? So you need to basically be aware of that, right? To distinguish, especially since JSON XML is a syntax. So be aware of the difference between the lexical space and the value space. The moment you have parsed and validated your JSON or XML document, you leave the lexical space and you are in the value space. And then you should think in the value space when you query your data. It doesn't matter what the lexical representation used to be in the original document. Here it's the number 4. Okay, here's another example with the value space, which is the lexical space for a date is 4 digits for the year, dash 2 digits for the month, dash 2 digits for the days. I think this one is called, I forgot. Oh, no, I know. The ISO 8601 specification. And again, I don't know why I know that by heart, but there is a specification that tells you that. You should really follow these because there are so many ways of expressing dates. Try to follow the standard ISO 8601 if you can, because otherwise it creates a lot of nightmares for the users if they have to parse dates in a different way. But again, if you write 20170801 in this way and you declare in your schema that this is a date, once you have parsed it, you are in the value space and you know that this is August 1st, 2017, right? Okay. And this is also the same standard, ISO 8601, with a T in the middle, and then you can have the hours, the minutes, the second, and Z is for the time zone, the UTC time zone, right? So this is it, okay? And then again, you abstract it to the value space on the left. Okay, yet another one, this is the lexical space for durations. If you have P, it's always P, then 1 year, 2 months, T, 3 hours. T is always to separate the days from the hours, and P basically says it's a duration. But again, if you declare it as a duration in the schema and you had this lexical value in JSON, the moment you parse it, then you are in the value space and you know this means 1 year, 2 months, 3 hours, okay? Then in many systems, you have the concept of subtypes. For example, an integer is a subtype of decimal because every integer is a decimal, but not every decimal is an integer, right? So you can have this notion of inclusion of value spaces. Typically, a subtype is a restriction of the value space, and a supertype is a larger value space. So these are the atomic types. Again, it's a menu. Not all the systems have all of the types. They will have some of them, not all of them. Some systems will have more of them. Some systems will have less of them. The correspondence is not always perfect, but this is pretty much the idea of what you will find. Now, let's turn to structured types. Structured types, typically, in many systems, you have maps and you have lists. The maps is what we call the JSON objects, but you could also consider that a set of XML attributes in the same element could also be seen as a map, from attribute name to attribute value. Structs in data frames, we'll see data frames later, but structs are also maps. And then lists is like a JSON array, is a list. An XML element can be seen as a list as well. You can have nested elements and text and so on. It's ordered, so this is why it's a list. And a data frame array would also be a list. So map and list, these are the mathematical terms, or let's call it the theoretical computer sciencey terms, map, list, right? And then on the right, they can be called many, many different names, but it's all the same, in fact. For whom is that clear? Maps, lists? So I might use that interchangeably. Sometimes I will say maps, sometimes I will say objects, structs maybe more rarely. Sometimes I will say list, sometimes I will say array. It depends on the context, but basically these are all a bit interchangeable, right? So map and list would technically be used maybe in more theoretical lectures about algorithms and data structures. Object and array would be used a lot in database lectures, technically. Okay. Yet another thing that many systems have in common, not all of them though, but many systems have the notion of cardinality. Why do we care about cardinality? Well, in many languages, we actually don't. Because if you consider a language like Python or Java, you only ever have a single value at the same time, right? In Java, you have a pointer to an object, but you always return, every function returns a single value. But there are systems like SQL, for example, that can return sequences so they can return 1 million values out of a function, like a whole table, 1 million records. In that case, the type system typically also allows you to state how long this output is going to be. And there are typical characters that are used for that. For example, 1 is very often, if you return a single value, 0 or more means arbitrary length. A common sign for that is the asterisk. That actually means any number, 0, 1, or more. 0 or 1 means either you have it or you don't. A question mark is typically used for that. It's 0, it's 1. It cannot be 2, though. It has to be 0 or 1. And 1 or more mean it cannot be 0, but it's at least 1. That's a plus, right? So the asterisk question mark plus. If there's nothing, typically it means exactly 1. In some systems, you don't use the asterisk, the question mark, and the plus. Instead, you use adjectives. For example, you could use required in order to say exactly 1. You could use repeated in order to say 0, 1, or more. Or you could say optional in order to say 0 or 1, right? So it really depends on your system. But in many systems, there is this idea of these 4 categories: 1, 0 or more, 0 or 1, 1 or more. Is anybody familiar with regular expressions by any chance? Some of you. So that might be easy to learn because these are actually the same symbols that you are familiar with in regular expressions: asterisk, question mark, and plus. Okay. So this is cardinality. We'll come back to that when we study query languages for JSON in a few weeks. We'll use them again. Okay. Now, look at that as if I gave you a huge dictionary with 20,000 words, and then there is the Zurich in the first column, Basel Dutch in the second one, Ostschweizer Dutch in the third one, Barn Dutch in the fourth one, and so on, except that now I do it 4 types. So this is an attempt. Actually, it was by popular request. Some people in a former class a few years ago asked me for that. It's an attempt to have a comparison of different type systems. So here, JSONic we will study, and JSON, that's a validation language, we'll study it in that course. JSON schema is also quite popular. XML schema is used for XML. Spark SQL, we'll cover it in a few weeks, also have a type system, data frames, in fact. PostgreSQL also have types. Python also has types. So these are plenty of them. There are even more than that, right? There's probably thousands of them. But what I did here is I tried to show you how it corresponds to each other, right? For example, so if you remember what I told you about atomic types, you will find a lot of what I told you, right? Decimal, integer, byte short, int long, I told you. Here, these are the IEs 754 double float for approximated real numbers, strings, booleans. These are the binary representations, base 16, base 64, dates, times, objects, arrays, and so on, right? So this is all I showed you. But here, you basically notice several things. The first thing you notice is that it's almost full. It means that there is kind of a correspondence between the two. For example, a double in JSONic is called a number in JSON schema, a double in XML, double type in Spark SQL, it's called double precision in SQL, it's called float, right? You need to be careful sometimes. This is called a float in Python, even though it's called doubles. But basically, very often you have a correspondence. The other thing you notice is that sometimes you don't. For example, there is no float in JSON schema. That doesn't exist. Base 64 doesn't exist in here, doesn't exist in there, and so on. So it's not perfect. And the other thing that you notice is that it's not always one-on-one. For example, byte short, int long, there's no distinction really in JSON schema. In PostgreSQL, there is nothing for this one. In Python, they don't even exist. You just have int and that's it, right? Int for actually any integer, and you don't have any distinctions. So again, treat it like dialects, have a general understanding of the type system. Now, basically, I can throw at you any technology, any schema validation technology, any programming language. I'm pretty sure you're going to learn it very quickly because you already have this general understanding. All you need to do is open the documentation and see, okay, oh, that type here exists, oh, that type doesn't, and oh, that corresponds to this, and so on. So you can try to fill that table with any new technology to see how it works, right? And you see here the dict corresponds to an object, the list corresponds to an array. In PostgreSQL, you have the array notation with the square brackets. Struct types in Spark SQL correspond to dicts in Python, and so on, right? It's not complete. There's probably more types that I forgot, but just to give you an idea. Right? Who feels this general type system thing, right? The intuition of that. Okay, many of you, that's my goal. And again, there's no way you can learn everything by heart, right? But basically, you understand on the high level how these things actually work. Okay. Then let me move on to validation then. So specific JSound is a schema validation language that was actually designed for teaching. It's a good way to introduce validation with that. And then once you know it, you can very quickly learn any other. This is the first column in there, by the way, JSound. These are all the names in there. By the way, I can already mention it now. If you look at the XML schema column, this is the same thing. There's this XS prefix, but these are exactly the same types in XML and in JSound. Okay, so JSound. So I'm just going to show you examples and then you will see the intuition. So what does it mean that we validate a document? First, it means that it's well-formed. Otherwise, we cannot validate it. So let's take a well-formed document. I'm going to put my well-formed document on the top of the screen. Last Einstein is my well-formed document. It's also called an instance, the document that I would like to validate. When I want to validate a document, I need a schema. The schema will be at the bottom. Last string, that's a schema. The schema gives me the constraints that I want to check. And then yes or no, does my document fulfill these constraints? But you might notice the first interesting property here is that the schema is also a JSON document. It didn't have to be, right? My schema could be anything else. In fact, there are technologies where the schema looks totally different. But this is very common in XML and schema validation. A schema validation language for JSON will typically be done with a JSON object, and a schema validation in XML will typically be done with an XML document. It's very common because it's intuitive. So what does my schema say in here? It says, I want to check, so last string, that's my schema. I want to check if the document that I'm looking at, first, that it's an object. Second, that if it has a key called last, then that has to be associating with a string, not an array, not a number, it has to be a string. So this is what I'm checking. Furthermore, I do not want any extra keys. If there are more keys than just last, that's not valid. Who believes the document on top is valid against that schema? More raise hands? Yes, it is valid, right? I have a key called last. It's associated with Einstein that is a string. So this is perfect. So indeed, what I can say is that my instance documents that I stored in the file.json on my hard drive is valid against the schema that I stored as a JSON document in schema.json. Here it's valid. Here's another example. In my schema, I say, if the key is last, then it has to be a string. If the key is first, then it has to be a string. And I have an instance that is valid against that schema, because last Einstein, that's a string. First Albert, that's a string. So that's fine, right? So my document is valid against my schema. My instance document is valid against my schema. Okay. Next, this also works. In that case, I want last and first to be strings. But again, I said, if they exist, because in that schema, I'm fine if it doesn't exist. For example, here, my instance document does not have any first key, doesn't have the key first, but this is fine, it's optional. So it's also the case here that my instance document is valid against my schema. Okay. Now, what if I don't want it to be optional? What if I want to say in my schema, it has to be there, last has to be there, first has to be there? Well, in the compact form of the syntax, just adding an exclamation mark does the trick, right? So if I say exclamation mark last, it means it's required, it has to be there, and first has to be there. So now my instance documents have to have these two keys, and it has to be strings, right? So again, my instance document on the top is valid against my schema at the bottom. Here's another one where I have last that should be a string, age that should be an integer. I removed the exclamation mark, so now they're optional again. And now it's valid, right? Age 142, that's fine, that's an integer. And last is Einstein, that's fine, it's quotes. Note that in the context of JSON, we don't care if there's double quotes or no double quotes when we parse that, meaning that even if there had been quotes around 142, it would still have successfully parsed as an integer, because we're only interested in the lexical representation, right? We're only interested in the lexical representation. Okay. Here, it's a Boolean. Physicists must be a Boolean. Yes, it's true. So this is a Boolean. Again, it would also have worked with the quotes, because TRUE is the lexical representation that is in the Boolean lexical space. Null, that's it. Location is null, so that's fine. It works as well. Location must be null. And that's it, right? Who understands the intuition here? Right? The idea and the way it was designed is that the schema actually looks very similar to the document that we are trying to validate. That's on purpose. It's meant to be intuitive in this way. Okay. Now, I already showed you a lot of the types there, but this is basically the menu that is specific to JSON, but also to XML schema. That's all standardized by the W3C. This is a list of types that you can use. There's a lot of them, even the unsigned, positive, negative, you have everything in there. Date, time, date, year, month, if you want to say, for example, April 2024, that's a year, month, and so on and so on. Durations, year, month, duration, hex binary, that's the basic 16 representation. Yes, maybe we can throw the... Oh, unions, you mean, right? So it is possible to specify union types where you can say this has to be an integer or a Boolean. So yes, many schema languages allow you to do this as well. That's a very good point. I just didn't put it on the slide to not complexify it too much, but it is possible to define union types as well. Okay. So you see, it's a huge menu here. It's a huge menu. It's all standardized by the W3C, and they are all available. And the list depends on the schema technology you're going to use, right? JSON schema has a much shorter list, for example. Okay, Now, how do we allow for any value? We can just use item. Item is a type that can be anything. It can be an object, an array, a number, a date, absolutely anything. So if you say location item, then you accept anything, and an array is anything, right? So in that case, it accepts Switzerland, US. You can also specify an array as an array of anything, and you use, again, it's very similar to how it looks in the instance document. Here, the square bracket item means it has to be an array with 0, 1, or more items, and the items can be anything. So in that case, we do capture a document like this that has a heterogeneous array. We just declare it as an array of items, right? If you want to be specific, you can also say, I want an array of integers, right? Now, this is an array of integers, 1, 2, 3, 4 in my instance document. And in the schema, it's very compact. Just use the square brackets with integer. That's how you specify your schema, right? For whom is that intuitive? Okay, very good. So you see, array of items, array of integers, and so on. You can also have arrays of objects that look the same. In that case, I have an array of objects that have an optional key foo, but it must be a Boolean and nothing else allows, right? It could also have an empty object that would be fine too, because foo is not required. So this is very useful if you want to nest a table in a table in a table, then now you can have an array of objects. And you can even have an array of objects inside an array of objects. Yes? Any other object that's not that anything else, or is it so the meaning, let me explain the meaning, and then you will tell me if that answers your question. When I put in my array, the square bracket means that it's an array of objects here. And this means that every one of the objects that is in there must have either one key foo or no key at all, but not more than that. That's the first condition. So if you had bar or anything else, that would be invalid anywhere. The second condition is that if it exists, the key foo must be associated with a Boolean. It has to be true or false. So I could have an empty object that would be fine, but apart from empty objects, I have to have foo associated with a Boolean, right? Even if I have 1,000 objects in there, they all must follow exactly that pattern. Did I answer your question, or is it still open? No, that would not work. So basically, oh, now I understand your question. This really says this is an array of objects. If you have anything else than an object, that's an error. It's not valid, right? So if here you had an integer and a string or a Boolean outside an object, that would be refused, that would be rejected, right? So this is very specific. It requires it to be an array of objects. Just like when you set here an array of integers, and if you have something else than an integer, it's not accepted, right? And we will see that this is very, very good for data frames. In fact, this is creating a data frame when you do that. Okay. Now, extra fields are forbidden by default, meaning you cannot have anything extra. In that case, you have last first, but if you had middle, then that wouldn't be allowed. Now, you know that there is another syntax to JSON that is a bit more verbose, but it allows you to do more things. Most of the time, you don't need it. I'm only showing it to you as an example because I don't require you to learn it. Just know that it exists, and if you use it, it can do even more things than the compact syntax. But basically, the idea is that instead of looking like the document, it's more verbose. Here, I basically explicitly say the kind of document I want to validate is an object. The base type is an object. The content of it is made of a key called last of type string and a key called first of type string and so on. It's the same thing, right? It's just that this is more verbose. But the nice thing about the verbosity is that you can do many more things. In particular, you can add closed false. And when you do that, closed false, you basically allow for extra keys that you didn't anticipate in the schema. In that case, I have year 1905. That's the great year for Albert Einstein. It's fine, right? Year is not in my schema. I don't have any name year in the content. But since I said closed false, then I allow for any other key, right? My only constraints are if there is a key last or first, they must be strings, but any other key is fine, and that other key can be anything it wants to be. For whom does that make sense? Okay. But this you can also only do with the verbose syntax. In the compact syntax, you don't have any way of saying that it's not closed, that it's open, right? So if you use the compact syntax, it will never allow for extra properties. Okay. And again, don't be scared by the verbose syntax. I'm just telling you there is one, but it's okay. So what did we learn with that schema language? The bells and whistles of a schema language. What can we do with a schema language? Well, the first thing that we can do is that we can be very restrictive about the values that we allow. For example, I can say in my array, everything must be an integer. Or I can say the value associated with that key must be a date, and so on. So I can restrict the types, meaning that I restrict the literal that I can have, the lexical representation. I can also cast, meaning that if I have an integer in quotes, but I parse it as an integer, then it drops the quote. It's kind of parsing it as an integer in memory, right? Note that in integers, for integers, the quotes are optional. For dates, you will need the quotes. You cannot put a date just like that without quotes in JSON. So a date will always be inside quotes, but in memory, you will cast it to a date. Cast means that you change the internal representation and make it something of type date, of type integer, and so on. That's called a cast. So in that case, it's a cast because we have the string 2134. We cast it to the integer 2134. This is done implicitly. When you validate against an integer, it's going to force the cast. This is what I called annotation earlier, basically. The third thing we can do is require a value. I can say foo is required, or I can say foo is optional. That's the third feature of a schema. A fourth feature is whether or not I allow for extra keys that I don't have in my schema. That's also something you can choose to do or not to do, right? You can, for example, either say bar, which is not in my schema, will be accepted or rejected. It's your choice, depends how you build your schema, but you can control that. What else? So that I didn't show you how to do, but there's the concept of default value. What is a default value? It's the ability to say that if the document is missing a key, then you're automatically adding something for it. For example, I don't know, imagine you have a list of students and there is a an optional key called university, and you can say that the default value of university is ETH Zurich. What it means is that if the instance document does not have any university key, then it's automatically going to add the key university associated with ETH Zurich. Then we say that ETH Zurich is a default value for university. That's also part of the annotation process. And after the validation, then you will have ETH Zurich added to the tree in memory. Something else that I didn't show you is the concept of primary keys, and this is particularly important when you start having denormalized data with tables in tables in tables in tables. You can, for example, have an array of objects that is meant to be a nested table, and maybe that nested table has a primary key. For example, foo here could be a primary key. What it means is that you don't allow repetition. Here you have foo2 and foo2. That's not allowed. You could reject it by saying that foo is a primary key within each array, right? This is also possible. I just didn't show you how to do that, but this is also something you can do. Okay. Now, here's another example, still JSON. This is a real world thing. So on the top, you have an instance of what's called the Great Language Game data set. It was, yes, there's a question over there. Do we have the microphone actually? So I can repeat then, yeah. Mm-hmm. Yes, you can, but with the verbose syntax. With the compact syntax, you can't. You can just say what the type is. With the verbose syntax, when you define an array type, you can say, for example, at least 4, at most 10. That you can do, absolutely. Mm-hmm. All right. So this is a real-world example. There was a game a few years ago. I don't know if you actually saw it. It was a game where it would play a sound, somebody speaking, and it asks you what language is that, and you get 4 possibilities. For example, in that case, it would play some Norwegian sounds, Norwegian words, and then it asks you, is that Maori, is that Mandarin, is that Norwegian, or is that Tongan? And then you need to answer. And basically what you have here is that somebody played from Australia, they were in Australia, and they said it's Norwegian, and they were correct. So the guess was Norwegian, and the target, which is the correct solution, was also Norwegian. So in that case, they won. And that was actually played on the 19th of August, 2013. And there is a data set like that. This was a real game. There was really a website where people could play. And actually, we played it in the Polymensa back then. It was very fun. And they collected data based on that. Every single play, they stored in a database. And I think they have 16 million plays. So there is a collection of 16 million JSON objects. This is one of the 16 million. You can download it. It's out there on the internet. We also use that. But basically, this is an example of data set that has a structure, because all of these 16 million objects, they all look like that. And the nice thing is that because of that, we can actually design a schema against which this is valid. And the way you do that is that all of them are required. They always exist. This is a string, this is a string, this is a string, this is an array of strings. This is hex binary. You see, this is a base 16 binary representation. And then this is the date right here with the ISO 8601 representation there with the dashes. And you see, this is the schema against which all the documents are valid. Who has an intuition for that? Normally it's supposed to be intuitive. Awesome. Okay, so this is JSON. Now, if you remember that document I showed you earlier, I claimed that that document is easy to build a schema against which it's valid. Who has it in their mind? Who could, in their mind, come up with a JSON schema against which this is valid? Take a few seconds. Raise your hand when you have it. I see some raised hands. Now tell me, is this what you have in mind? Who had that in mind? Or close to that? Okay. So you see what happened here. First, I made them all required except bar. Bar is the only one that doesn't have an exclamation mark because this one has to be optional. A, B, C, foo, they're all required. A is an integer, right? B is a Boolean. Foo, so C is an array of objects. And inside the array of objects, foo must be a string. And bar must be an array of longs. Why long? I just wanted to have fun. I could have put int, I could have put integer, whatever I want. But anyway, this is the idea. This is one possible schema against which this is valid. And the idea is that this is an example document, but once you have a schema like that, then you can build a collection with 1 billion documents, and you can require that each one of these documents is valid against that schema, right? This is the idea. But the cool thing is that it's optional. You don't have to do it, and you don't even have to do it at the beginning. You can do it later. You can first put your documents in there, and maybe a week later, come up with a schema and then validate, but it's fine to do it later. In PostgreSQL, you cannot do it later. You have to do it now. In PostgreSQL, it will not even let you not do it. You have to do it. Now, this you can go to, it's an address. You can type it right now in your browser if you want, public-rumble-db.org 1990 JSON-validator.html. You can put some JSON, you can put some JSON and some JSOUNds, and you can play with it, press a button, and you get green or red, depending if it's valid or not. This runs in the clouds. There is an instance of RumbleDB running in the Amazon clouds. It's restarted every day. If it goes down, just wait a little bit. It's supposed to restart automatically, and it should scale by putting more machines if more people connect at the same time. But just be aware that the machine running that only has 1 gigabyte of memory and just a single core. Yes? I have to, let me see. Ah, yes. So you could indeed have said that C is an item. You could also have said that C is an array of items. This is all fine. But in practice, you basically want to be as restrictive as possible, but not too much. You have to be restrictive in the sense that if you put C that is an item, then what might happen is that if you have C associated with something else, then that will be accepted. So the question is, do you want to accept it or do you not want to accept it? This is the question you need to ask yourself. However, what you need to keep in mind, and I'll come back later, is that this here, for example, can be used with a data frame. This is basically what I call data frame friendly. It's a data frame friendly schema. You can put that in pandas, it will work. Well, not with that syntax, but you can create a pandas data frame in this way. However, if you design your schema and you put item instead of C, that is no longer a data frame. Because in a data frame, you have to be specific. In a data frame, you have to say what's the type of every column in most of the technologies. There are data frames that have something called variants. Maybe you heard of the variance types in databases. Variants would be the idea of item, of anything, but it's hard to optimize. So this is why in practice, you should try to avoid using item. If you can, try to avoid it. Try to be specific. Okay? Did it answer your question? Yeah. All right. Okay. So yes, go to that page, play with it. You can use it all you want. It's also integrated in, so there's a JSONic tutorial, but there is also a JSOund inside JSONic. There will be an example in the exercises, but this is the idea. So now you can play with it all you want and make it work. Okay. You see, there's always this port of 1990, public-rumble-db.org. That's the one that is running on Amazon for free. It's just for everybody in the world to use. If you use the Jupyter Notebook inside the Docker, who did the weekly tutorials of JSONic? Who tried them? Some of you, right? Then you will see that then it's not public rumble-db. It probably says rumble 1990. This is because it's inside Docker. If you see localhost, then it means you're outside Docker, but on your machine. Localhost, normally you should not use, right? If it's localhost, then something's probably wrong. But within the Docker that we use in that lecture, it should just be Rumble 1990. Okay. All right. That's the sandbox. Any questions on JSOunds? Okay. So now, JSOund is easy for teaching. I'm going to introduce you to JSON schema, which is the very popular one. And you'll see the comparison. It basically does the same thing, more or less, with a few differences, but this is the idea. First, you notice that it's a bit more complex. It's closer to the verbose syntax of JSOund than to the compact syntax, so it's a bit more involved. But basically, the idea is that here you say the type must be an object, and the properties of that object must be last, the type of which is string, right? This is what it looks like, basically. That's it. You just have to accept it the way it is. This is what the JSON schema looks like. And then on the top, that document validates against that schema. Again, that's no longer JSOund now. It's JSON schema. That's a different technology. But you notice it still looks like a JSON document. The schema is still in JSON. Here's another one where you say last must have the type string and first must have the type string. So it's valid again. Here you also have the same idea that it's optional by default, but if you want to require it, you just put required in there after the type, and you have a list of the keys that are required. So you see, it's the equivalent of that exclamation mark in JSOund, but instead of an exclamation mark, you just have to list the keys that are required. In that case, we say last and first are required. Okay. Then extra fields, so this is unlike JSON, extra fields in JSON schema are allowed by default, but you can say additional properties false, that's kind of like closed true in JSON that basically says you don't allow any additional properties. So you say in that case, only last and first are allowed, not anything else. But if you don't have it, by default, it will allow them. So you see, every technology might have different conventions, but they can still do the same thing, right? They have the same power. Now you can have age, the type of which is number. Just be aware here that the list of available types is much more restrictive in JSON schema than it is in JSON. In JSON, you have this whole menu of types that is standardized by the W3C. In JSON schema, you can just say number, and you have patterns. You can control the patterns, but you just have to say number. There's also Booleans. You have null also that you can say. You can also, so here I have no idea why it's designed that way, but if you put true, it allows anything. True would be the equivalent of item in JSON. I have no idea why. False means you disallow it. So here false means location is not allowed, right? So it might be less intuitive, but this is just the convention under which it's designed. Here you have an example of pattern. They are also allowed in the verbose JSON syntax, but here you say these must be numbers between -90 and 90. This is the latitude on the Earth, right? Sorry, north-south. -90 is the North Pole. Sorry, 90 is the North Pole. This is the South Pole. And here, this is the one crossing Alaska, right? 180, 180, -180, the longitude. So you can restrict in that way with patterns. You can also say that you want an array, then you just use the array string, right? The type must be an array of anything. You can also specifically say that you want an array and each item must have the type integer, then you write items type integer. Again, it's a bit more involved, it's a bit more verbose, right? You just have to learn it or read the documentation, but basically it can do the same thing. It's able to say that you have an array of integers, right? But you see how quickly I went over JSON schema. Why? Because it has the same features as JSON. So I took the time with JSON with the intuitive syntax. JSON schema, just go over the slides again offline. You will quickly notice it does exactly the same thing, just with a different syntax. Okay? And that I keep for next week for XML schema. But again, now that you know how JSON schema works, I'm pretty sure XML schema would also be just as easy for you to learn. All right? So the reminder we'll do next week. And next week, we'll probably start with MapReduce. With a bit of luck, we'll have time to start with MapReduce. So thank you very much, everybody, for attending in presence or on Zoom. Enjoy the exercises that are prepared to the TA team. I think there was a bug in one of the exercises with HBase, but the deadline got extended. Don't hesitate to write if there's any issue, right? And we basically listen to support you. Have a great day and see you next week at 8 a.m. for the next lecture.